I'm going to talk about the SiFive Apex brand that Yunsub talked about in his keynote. So introducing scalable new core IP for mission-critical use. I'm Murali Vijayaraghavan. I'm the principal engineer leading the formal methodology group at SiFive. Let's get to it. All right. So the mission-critical SoC market or IP core market is pretty substantial. You have the automotive industry, the avionics, the industry, robotics, and the medical devices industry. And each of them have their own standards to meet the safety and security requirements. But all of these standards have several things in common. So let's go through the common requirements using the example of the automotive safety certification. So first and foremost, the condition is to have zero design bugs or systematic failures. This is one of the holy grails for verification, to make sure that the designs don't have any bugs. And that's an absolute requirement in terms of mission-critical use. For instance, if you have a medical device which has a bug at some point, it's going to kill humans and so on. And the second important requirement is the functional safety, which is defined by the ISO 26262 standard for automotive industry. What this standard basically warrants is that you should have low transient errors in your system, low random errors in your system. And even if you actually have errors in your system, it should fail gracefully. In fact, they define several grades of integrity levels called automotive safety integrity levels, ASIL ABCD. You might have known it by that name. And this defines the number of random failures that are acceptable at a given time. For instance, the ASIL D specifies that you should have less than 100 failures over, I think, 1 billion hours of operation. And finally, with the advent of wireless technology and generally computers controlling cars and so on, ADAS systems, we want to have it hacker-proof. That is, somebody should not be able to hack into your car and make it crash or whatever. So there are security standards too. So in legacy architectures or legacy way of building systems, the processor cores are actually built to optimize power, performance, and area. And then eventually they are retrofitted to have the functional safety aspect to it. And then you certify these retrofitted cores to make sure that it passes the functional safety standard requirements. But in SiFive, we are designing a brand new methodology for building this functionally safe and secure and correct systems from the ground up, the SiFive Apex brand. And these go well beyond the PPA. In fact, we can guarantee 100% adherence to the functional specification. That is the new formal verification methodology, which I'm going to talk about next. And we also design it from the scratch to take care of functional safety requirements, that is transient failures and so on. And we also will be using the technology which we get from SiFive Shield and SiFive WorldGuard to ensure security of these newly designed processors. And let's talk about formal verification, because that's one of the most important requirements in order to guarantee mission-critical use. What happens if we use traditional verification like simulation-based testing and so on? You cannot guarantee 100% coverage, because it takes a lot of time to even develop test cases to cover all the corner cases, and even then, you will miss quite a few corner cases. Nobody can certify that a particular IP is actually correct by just randomly testing it, or even directed testing or semi-random. Whatever sort of testing you do, there is no 100% guarantee. In order to overcome this, industry has somewhat embraced model checking as a panacea to solve all these problems. You have very little human effort. In the sense, you just push a button and it does a state space exploration or a symbolic evaluation to tell if a design is correct or wrong. It gives you 100% guarantees, ostensibly, and it, as a result, reduces the time it takes to achieve 100% functional correctness. But in reality, that is not the case. Model checking also suffers from the same kind of problems. The bounded model checking based tools such as Jasper Gold and VC Formal and so on. The reason why it doesn't scale that much is because model checking tools do a state space exploration and they don't scale well with the size of the system. So if you have a really large system or a really large state space, then the model checking tools kind of die on you. And so as a result, you won't get 100% coverage even if you use model checking based techniques. You have to put in a lot of human effort to break the problem into smaller problems, to inject invariants and so on, which are all cumbersome. So it's no longer a push button technique which provides the promise it has promise it has given, which is 100% guarantee with zero human effort. We are going to be using this new proof assistant based methodology, which is going to actually give you 100% guarantee about functional correctness while having medium human effort, as opposed to a large amount of human effort like model checking. And as a result, we can reach the desired functional coverage metric at a much faster rate. And this technique is called CAMI, which is a new methodology which was originally developed in MIT, and we rewrote that in SiFive. And this methodology, I'll briefly explain how this methodology works. You start with a RISC-V ISA formal specification, and then you also write a RISC-V a core implementation in the same language, the CAMI language. And then you write what is called a proof certificate, which essentially tries to give a proof in some machine-readable language that the formal specification is met by the implementation. And then you have a machine checkable proof. You have a machine check which actually automatically checks if this proof is correct or wrong. So as soon as a human provides a proof certificate, which is not a completely automated process, even now, that's why it's semi-automatic, the machine will automatically check if the proof is correct. As soon as the machine checks that the proof is correct, there is a 100% guarantee that the implementation meets the specification. And then this implementation is actually in the CAMI language itself, right? So we have a compiler which is also formally verified using the same technology, same underlying technology, which is based on proof assistant, to generate Verilog code. So if you notice, there is a link which links the formal specification of the RISC-V ISA all the way to the generated Verilog RISC-V core. And this means that the implementation, the RTL, is actually correct with respect to the specification. And all of the specification is open source. The language is also open source. So the colors didn't turn out very well on the screen, but I will be sending a PDF so you can take a look. The language is called CAMI, and then RISC-V spec formal is the RISC-V ISA specification that we developed in SiFive. These are all open source repositories which you can go and play around with. This actually generates Verilog. Even though it's a specification, you can actually generate Verilog, but it will use SRAMs for physical memories and so on. So it's going to be a single cycle specification which will not be practical as an implementation. All right. So, and how do we ensure that the specification is correct? Why do we need to ensure that the specification is correct? That is because with the same formal specification, we are going to generate or write different implementation and prove the correctness of these different implementations against this formal specification. For instance, the embedded simple core, like the E2 series, not exactly the E2 series, but an equivalent of an E2 series written in CAMI, or we can have a course with address translation mechanism, supervisor mode support, or we can have course with physical memory protection support and so on. All of them are verified against this or formally proven against this formal specification. So this formal specification has to be rigorously tested and validated. In fact, we have to validate it against the formal specifications. So the RISC-V formal specification that's shown in the green box is actually part of the formal specification task group. One of the 4 or 5 formal specifications which were developed as part of the task group. And then all the other formal specifications also have to be validated against this particular specification using bounded model checking mechanisms and so on. It is possible to find errors in the specification, which will again show up in the implementation. But so the biggest difference is we have moved the verification problem from verifying each and every single design that comes out every year or so on to the green box. You verify the spec once, and it's guaranteed to be correct for every single implementation from then on. So that's how we solve the verification problem. And in fact, we go beyond that. Instead of verifying a single instance, single in-order core or a single in-order core supporting the application processor and so on, we actually use this technology to verify generators, because generators is king in SiFive. And we can have an in-order core generator, which can be instantiated directly to an embedded 3-stage pipeline, or the same generator can also be instantiated into a 8-stage in-order pipeline with virtual memory support, that is an application core. We can also verify an out-of-order core generator, a three-way superscalar out-of-order core can be instantiated from this out-of-order core generator, or you can instantiate a 4-way superscalar and so on. There are several possibilities which you can instantiate from these generators. And each of these instances are guaranteed to be correct because the generator themselves are proven to be correct. So this is our new methodology for formal verification. And to recap, the existing methodology involving model checking or traditional verification does not give you 100% guarantee. It has medium to high human effort. Best case, it's just medium, and it's slow to achieve functional correctness. Whereas in Kami-based methodology, we borrow all the properties from the proof-assistant-based formal verification, so it still reaches functional correctness guarantees really fast, gives you 100% guarantee, and it has only medium effort. And on top of it, it enables us to prove generators, whereas the other techniques do not enable us to prove generators. This is the point at which I should be dropping the mic, but I'm just going to hand over to our functional safety partner, WrestleTech, who will talk about the functional safety requirements which are going to be enabled in our process. Thanks.
Thank you, my friend. Good afternoon, everybody. My name is Francesco Brancati. I'm very glad to be here on stage today. WrestleTech is becoming nowadays a key partner for everyone who would like to achieve functional safety in their mission-critical product. We are active in several mission-critical domains, from railway, automotive, industrial, and so on. And we are providing services about safety management. So what does it mean, safety management? It means we are providing services from the design of safe system to the verification, validation, and safety assessment up to the certification. And we are providing these services to our customers all over the globe. And we are very proud of their satisfaction that is also proven by the fact that we are receiving more and more ask for new services in these days. But why I'm here today? I'm here today to announce our partnership with SiFive. We are going to provide our services to SiFive in order to enabling them in achieving functional safety on their mission-critical product. But what does it mean, support? Support, it means that we are made available to them our skilled team led by more than 20 years experience key people in safety assessment. Our teams are multidisciplinary, so we have expertise both in CPUs, SoCs, but also on software at micro level and system level. And we are tackling time to market by using state-of-the-art tools and methodologies, and also custom tools and methodologies. But not only. Our support will not expire during the development life cycle. So our support will also be after the product release. We will be next to SiFive, providing help to SiFive customers when they have to integrate their solution. And so we will help them in achieving safety compliance when integrating their product and safety metrics and so on. So that is what will go to be happen, and this is how we will make it possible. Thank you, my friend. The stage is yours again.
Thank you.
Thanks.
Thank you, Francisco. So in summary, we are building a brand new blueprint for mission critical cores in SiFive from the ground up. And this involves using brand new methodology for formal verification based on this KAMI. And we will be introducing the SiFive Apex line of products over the next year, along with our leading partners and customers. Thank you. I'll take any questions. Yes. So the whole tool, the language and the underlying tool is released as an open source product in the website which I just mentioned. So you can actually go and use the tool yourself. In terms of properties, it can potentially prove properties too, but the way we use the tool is to prove full functional correctness. Instead of having individual properties like assertions and so on, we actually have a model which represents the specification of the entire system, and then we prove equivalence of these two systems. So that is feasible. You can actually create a proof certificate in using the tools to create this equivalence. But you can also perform assertion checks if you wish. We don't use it that way, though. Yeah. Right. So yes, the specification has to include all the parts that you're interested in and verifying that this is correct or formally proving that this is correct. In fact, in our specification, we do have an interrupt controller and so on as part of the specification, which is not just ISA specification, it's the entire surrounding stuff too in the specification. Plus all the devices which we currently support in this methodology, which is the interrupt controller and so on, yes. No, it's not true. We can only prove functional correctness. We can only prove assertions about, so if you say this happens within so many cycles, yes, you can prove that. But you cannot say, oh, this has a throughput of 1 IPS or 1 MIPS or whatever. You cannot prove anything about power. This is purely at least not yet. We may be able to extend it later. Go ahead, last question. For the lowest profile chisel generated designs, they are comparable, though KAMI generated ones are bulkier in some sense. We don't have, I mean, we'll be releasing those products soon, and we'll be giving the PPA numbers when we release them.